Let's take a look at solving systems of equations using substitution. When we are using substitution, what we want to make sure we have is we have one variable of our system has to be expressed in terms of the other variable. So in this case, I have x being equal to a quantity, and that quantity is y plus 1. Because x is this amount here, then I can confidently substitute y plus 1 wherever I see x in the other equation. So here, the equation says x plus y is equal to 4. So let's substitute in this value here where the x goes. So that would say that y plus 1 plus the y. Your book suggests to put the substituted value in parentheses, but that's equal to is equal to 4. So now I just solve this however I would. I don't need these parentheses since I'm not distributing anything. So I could say that y plus 1 plus y is equal to 4, or 2y plus 1 is equal to 4. I could then subtract 1 from both sides and show me that 2y is equal to 3, in which case we would divide by 2 and say that y is equal to 2/3. So we know that in our solution to this system of equations, the y value is 2/3. I'm sorry, 3/2. So now let's solve for the x. In solving for the x, all we do is substitute now our new y value, our newly discovered y value, into one of these two equations. Let's go ahead and use this one again here. So x is equal to 3/2 plus 1. Well, we can understand 1 to mean 2/2, right? So all we're doing is adding 3 to 2/2. So it's x is equal to 3 plus 2/2, which is 5/2. So our x value, where these two lines intersect, is 5/2. And that bears fruit when we check to see if these make both of these statements true. Is in fact 5/2 plus 3/2, is that 4? Does that make a true statement there? Well, as long as 5 plus 3 is 8/2, as long as that equals 4, well, yeah, 8 divided by 2 is 4, and 4 does equal 4, so we're good there. We know that this point is a solution on that equation. And we could try it with the other equation as well. Does 5/2, is that the sum of 3/2 plus 1? Is that the case? And we will see that, well, 1 is 2/2, and so yes, indeed, 5/2 is equal to 3 plus 2/2. That's true as well. So what that does is that gives us what our solution is. We have the solution to the system of equations, and what we've done over here is checked them, and everything came out kosher. And you might be saying, well, that's all fine and dandy when x is equal to a phrase over here, or y would be equal to a phrase. That's all pretty easy. What if I had a system of equations, however, that looked like 2x plus y is equal to 6, and my other equation was 3x plus 4y is equal to 4? Well, it's just as easy for us to take one of our equations, I'm going to choose this one, and solve it for y, right? It's easy to go ahead and subtract 2x from both sides, and what that would give us is, those would cancel, that would give us y is equal to negative 2x plus 6. And now we can go ahead and substitute this whole value in for the y in the secondary equation. So it would look like 3x plus 4 times the quantity negative 2x plus 6 is equal to 4. And then we go about our business doing what we know how to do. Minus 8x, positive times a negative is a negative, 4 plus 24, and that's equal to 4. Now we can use our rules of engagement to solve for x in this case. Scroll down, need some more space. Minus 24 from both sides. Cancel -5 is equal to -20, -5x, right? Divide both sides by -5. -5. X is equal to 4. Cool, x is 4. So now I can substitute that back in to one of the two equations. Let's use this one here. Let's use that one there and say that 3 times 4 plus 4y is equal to 4. So 12 plus 4y is equal to 4, which means that 4y is equal to -8, which means that y is equal to -2. So this is our solution to this system here, would be 4, -2. And again, if I were to substitute those values in to both equations, they should work, and that's how I solve a system of equations by substitution.